about all the things with springs? Locks, clocks, mattresses and sofas, pens, devices that hold batteries, trampolines and toys. Springs are so important, they have their own sound effect. In physics, there's a set of scientific laws surrounding springs that involve elasticity, torsion, and force. All of those come into play with springs. That's what British physicist Robert Hooke figured out in the 1600s. Hooke's law helps explain elasticity. It states that the force needed to extend or compress a spring is proportional to the distance that it's stretched or compressed. All springs, whether it's a rubber band or a slinky, have a natural position based on how they're made. Some, like this slinky, are naturally compressed. So when you stretch them, they want to spring back into the compressed shape. A spring on a garage or a porch door are naturally compressed. Mattress springs and springs in some ballpoint pens are compressed springs. Whatever the spring's natural position is called its equilibrium position, where it's either not stretched or not compressed, depending on the type of spring. So here's the equation. F sub s equals negative k times x. F sub s is the spring force, and it's measured in joules. Once it's stretched or compressed, how much the spring moves or is displaced is x, which is measured in meters. The k is called the spring constant, which is how the particular spring behaves. The units for that are newtons per meter. The x is a negative value to show that once the spring is displaced by a force, for it to spring back to its equilibrium state, the displacement is opposite the direction of the initial force. So, if you pull down on a spring, the spring moves downward, but when you let it go, it springs back in an upward force due to the elasticity of the spring. That's the negative kx. This is why the spring force is also sometimes called the restoring force, because it wants to restore the spring back to the equilibrium position. Whenever you do a problem with springs and elasticity, it's always important to remember to note the direction of this restoring force. We're going to use Hooke's apparatus, named after Robert Hooke, to demonstrate springs and all they can do. To see how much a spring stretches or compresses, let's get some spring action by adding some weight. Remember, weight is the mass times the acceleration due to gravity, g. With weight added to a vertical spring, let's see how much it stretches or compresses. Now let's add a heavier weight and do this several times. Each time you add weight, plot the spring action on a graph with force on the y-axis and displacement on the x-axis. How far does the spring stretch or compress? Check it out for yourself. You'll find that it's likely to be a straight line. The slope of this line is the spring's k constant. You might also discover that not all springs follow Hooke's law perfectly. When the force needed to compress or stretch a spring by a given displacement is linear and abides by Hooke's law, then the spring is considered Hookean. In real-life situations, the ideal springs are called Hookean and non-ideal springs are called non-Hookean. Rubber bands, for example, are non-Hookean. What does that mean? When the force needed to compress a spring by a given displacement is not linear and does not abide by Hooke's law, that spring is considered to be non-Hookean. If a spring is stretched too much, it loses some of its springiness and becomes non-Hookean. In that case, that straight line on the force versus displacement graph becomes a curve. Now, what if we pulled on one of these weights and there was no friction to stop the springing action? It would continue to bounce up and down forever. That same thing is true of a horizontal spring. This is called simple harmonic motion, and we will explore this idea in a later unit. Let's pull the spring away from its equilibrium position. Now, we have spring potential energy since we know it will spring back into its equilibrium position. Here's the equation to figure out the amount of potential energy in the spring. Pe sub s, that's the potential energy of the spring, is equal to 1/2 k, the spring's constant, times x squared. X is the displacement we've pulled the spring away from the equilibrium in meters. And the potential energy is in joules. So we can relate the spring's potential energy to gravitational potential energy. From another segment, you learned that gravitational potential energy is due to the change in vertical displacement. So if the spring action is vertical, you're dealing with both spring and gravitational potential energy. They're related to each other, and here's how. Remember the gravitational potential energy, written Pe sub g equals mgh. That's mass times gravity times height, which is just the force times distance. When I drop an object, work is done. Gravitational potential energy is converted to kinetic energy. In other words, the initial gravitational potential energy equals the final kinetic energy. The same applies to a spring's potential energy and the work it can do once the potential energy is converted to kinetic energy. A spring's potential energy can be converted into kinetic energy, and in an ideal world, this would be done conservatively, without energy transformed into heat by friction. The equation would look much like the equation you learned for the conservation of energy. When you stretch a spring vertically, the potential energies of gravity and of the spring are included along with the kinetic energy of the spring, so that the initial spring potential energy plus gravitational potential energy plus kinetic energy equals the final spring potential energy plus gravitational potential energy plus kinetic energy. For springs that are stretched or compressed horizontally, the equation looks much the same, but you can cancel out gravitational potential energy on both sides since the spring isn't moving in a vertical direction. Let's go back to the graph. If you want to know what the Pe is when the spring is stretched or compressed by a certain amount, pick a point, the displacement, on the graph and calculate the area of the triangle that it makes. Since the area of a triangle is half base times the height, and that's the same as half kx squared, you get the same answer as the average of the potential energy, which is 1/2 times the Pe final minus the Pe initial. It's another way to figure out the spring's potential energy. So now you know the relationship between spring potential energy and gravitational potential energy. The key to understanding physics is being able to relate the various forms of energy to one another mathematically. That's it for this segment of Physics in Motion, and we'll see you next time.
For more practice problems, lab activities, and note-taking guides, check out the Physics in Motion Toolkit.